Alright guys, in this lecture the primary objective is to help you understand the differences in vehicle architecture between an IC engine vehicle and an electric vehicle. So once we have understood that, we want to make sure that you understand the functions of key components of an electric vehicle. Again, the objective here is to not offer in-depth explanation for each and every topic, because I don't think that's possible in a short course, but we try to highlight the functions and engineering behind key components that are unique to an electric vehicle. And once we have done that, we will be diving deep into battery packs. We will essentially focus on the different configurations of battery packs and also talk about why these configurations are needed. Once we have done that, we want to make sure that you understand fundamental electrical concepts, because that's extremely important before you try to understand the performance parameters of a battery pack. So let us all first start out with the architecture of a gasoline vehicle. And I'm assuming this is something that most of you are familiar, right? So you have a fuel tank in the back and you have your engine at the front, right? So most of the modern engines have a fuel injection system, and the amount of fuel that's injected is basically controlled by the ECM, which is the electronic control module or the onboard computer. The power that's produced by your engine is transmitted to the wheels via the transmission, and in some cases there is a propeller shaft that runs from the front to the rear. Exhaust gases that are produced because of combustion are emitted out through the exhaust system, which essentially leaves the vehicle through the tailpipe, right? And your gasoline cars has a small battery pack, typically a 12-volt battery pack, which is responsible for running the starter motor and powering auxiliary systems like blinkers, indicators, and other electrical equipments which actually operate when the engine is turned off. Now, in contrast, if you look at an all-electric vehicle, the primary difference is the traction battery pack, which is placed at the bottom of the vehicle, right? So this occupies a large amount of space and also weight, and this is kind of the main differentiator, right? So with respect to the battery pack, the idea is that's your primary energy source, and from the battery pack, the energy has to go into the traction motor. Now, if you're using an AC motor, you need a device to convert the DC current from the traction battery pack to an AC current, and that is where an inverter comes in. Now, in addition to this, electric vehicles have something called as a DC-DC converter. So the idea is again very simple. You have a lot of power electronics components that are mission critical, and all of them require different DC voltages. So a DC-DC converter is essentially an onboard transformer which converts the voltages to the respective value depending upon the application use. And then in addition to this, you have a charge port which is basically used to charge the onboard batteries. And in addition to this, right, you have a strong cooling system. Now, in case of a gasoline vehicle, the thermal system, the cooling system is primarily used to cool the IC engine. But here, there are so many things that you need to take care of. You need to make sure that all the power electronic components and batteries are maintained at reasonable temperatures, because all these components are sensitive to temperature and their efficiency drops pretty badly if their temperature exceeds beyond their normal range of operation. Then finally, we take a look at a hybrid electric vehicle. A hybrid electric vehicle essentially contains all the components. Now, the primary difference is that the engine and the battery pack and the electric motor are going to be comparatively smaller when compared to an all-electric vehicle or compared to a conventional IC engine vehicle, right? But overall, it contains pretty much all the components that an electric vehicle would have, right? And it also contains components that a gasoline vehicle would have. And you can kind of see that from this particular picture. Now, with respect to key components that you should remember from this course, first is battery, right? Again, with respect to battery, we have a dedicated lecture on it, so we'll give you more details. Obviously, the electric motor. See, the electric motor is essentially what converts the electrical energy from the battery to mechanical energy. Then you have your power electronics controllers. So these are essential hardware that controls the speed and torque, right? Now, in an IC engine vehicle, you have your fuel injection system, right? Whereas in electric vehicles, your power electronics controller is responsible for controlling the speed and torque. Then you have your thermal system. The thermal system, as I mentioned before, makes sure that the engine, motor, controller, DC-DC converters are all maintained at the right temperature. And with respect to DC-DC converter, it essentially converts high voltage from the battery pack to a lower voltage that is required by other accessories. Now, in this particular course, the power electronics controller is not covered. With respect to thermal systems, the battery thermal management system is covered, but cooling of electric motors, cooling of DC-DC converters, and then radiator design is not covered. And then finally, DC-DC converters are also not covered. So now let's take a look at a battery pack. So essentially, battery packs provides direct current, right? Or also called as DC power. Now here we have a simple made up battery pack which contains 4 cells. Now these cells are connected via bus bars, and you generally have an onboard BMS. A BMS stands for battery management system. It is quite different from a BTMS, which stands for battery thermal management system. BMS is essentially the manager. It makes sure that a charge and discharge processes occur as per set operating conditions. You don't want the battery to be charged too fast. You don't want it to discharge too fast. You want to make sure that for mission critical application, the BMS also integrates a notification system to let the operators know about critical performance loss. Now, battery packs come in different sizes and shapes. Not all battery packs require cooling. So for example, in this particular case, you can see that the cells are actually packed inside a plastic container and you really don't need to cool it, right? That's probably because the total operating voltage is very low. On the other hand, you can actually have battery packs in different forms. For example, here you can see that there's a battery pack with a rigid enclosure, and it also has a cooling fan, and here's a vent which is basically used to remove the heat generated from the batteries. Now, if you basically think about batteries that are used for automotive applications, you essentially use cells which are then combined to form modules, which are then combined to form packs. And in terms of cooling, we generally see that for automotive application, liquid cooling is preferred because that gets the job done in an efficient manner and in a compact manner. So the idea is very simple. Here I have a simple 2-cell battery pack with a made up liquid cooling system. So ideally you don't need liquid cooling for a 2-cell system, but here we just wanted to give you the idea. So you can see that there's a cooling jacket which kind of wraps around the 2 cells. You have cold fluid going in through the blue inlet. As it goes through the cooling jacket, it takes in additional heat that is generated from the batteries. And when it comes out on the other side, it comes out as hot fluid. Now, if we can extend the system a bit more, you essentially have a large battery pack that's typically found in an automotive application. So here you can see that we kind of repeat the same structure 6 times. So this structure here, which contains several cells, is what you call as a battery module. So in general, for automotive applications, what is desired is you group cells into modules and you have multiple modules that form a battery pack. And this is advantageous in several scenarios. For example, say that the BMS detects there are certain cells that are at fault. You don't have to worry about replacing or removing the entire battery pack. You might just replace or remove a single module. And from an operational voltage point of view, automotive battery packs have really high voltage. So if the modules are smaller, so the risk of having an operational hazard while operating on a battery module is less because the operational voltage per module is going to be low. Again, the drawback of having more modules is increased manufacturing costs. You will have more interfaces between the different modules, and that can cause problems on its own. Ideally, it's a trade-off between safety, performance, serviceability, cost, and many other parameters. Anyway, so here in this picture, this is what you would call as a battery module, and you combine multiple battery modules to form a battery pack. All right, I hope that makes sense. And as I mentioned slide back, typically when you are thinking about number of modules and number of cells per modules, these are the things that you look at. You look at safety, performance, serviceability, and cost. And depending upon the industry that you're working for, these parameters would change. Alright, so that being said, if you want to learn more about batteries, understand battery ratings, you need to have strong fundamentals in basic electrical engineering concepts. As we all know, batteries store chemical energy and they convert them into electrical energy, right? Electrical energy is nothing but electricity, and electricity is nothing but flow of electrons. An electron is essentially a charge, right? So charge is essentially a material property and the unit of charge is coulomb, right? So the charge of an electron is minus 1.602 E minus 19, right? And similarly, the charge of a proton is positive 1.602 E minus 19. So these are things that you might have studied in your high school physics. Now with this, what you can do is you can figure out the number of electrons that you would need to have a charge of 1 coulomb, right? So that would be 1 divided by this number, which is going to be really huge. Now, when 1 coulomb of charge flows per second in a wire, then the current through that wire is called as 1 ampere. All right. So we know what 1 coulomb is. 1 coulomb is nothing but 1 divided by 1.602 E minus 19. That many electrons. So if that many electrons flows through a wire per second at any given point, then the current through the wire is said to be 1 ampere. All right. Now, the other important thing that you need to learn is volt or voltage. So voltage is essentially associated with the work done per unit charge. So if we say that a battery has higher voltage, then what it means that higher work is available to move a unit charge. In other words, you have the ability to move more charge, and since movement of charge is current, you can essentially say that with higher voltage, your current through the circuit would also be higher, provided the resistance offered by the circuit is the same. And that is essentially the law V equal to IR. Voltage is equal to current times the resistance. So to kind of reiterate on that example, let's say that you have a 2-volt battery. The amount of work input to move a charge is 2 times more than the amount of work input when compared to a 1-volt battery. In other words, a 2-volt battery will move 2 times the amount of charge as a 1-volt battery, right? Since it's able to move 2 times the amount of charge, you can essentially say that a 2-volt battery will have 2 times more current than a 1-volt battery. Like I said, this statement is true only if the resistance offered by the circuit is the same in both the scenarios. So in order to kind of understand these concepts a bit more, and also to understand a few more concepts like charge flow, capacity, rate of charge flow, and then to understand need for DC-DC converter, we have created a very simple example, and I like to call this as a candy machine example. So this is a made up candy machine. No real candy machine looks like this. How essentially you have a bowl here which stores a lot of candies, and you have this box here, and then you have a curved elbow connector which connects the reservoir of candy to the boxes, right? So here are the key concepts. So current is essentially going to be the rate at which these small balls flow, right? So in other words, if you assume that each of these individual red balls is a charge, the rate at which these red balls flow is what you call as current. And potential difference is going to be the difference in electron in particle density in the reservoir and the right hand side, right? So initially, if you can imagine, the candy jar would be full of candies, right? So it would have more balls on this side and you would have no balls on this side. So that is when the potential difference is maximum. So it is almost very similar to how water flows from an overhead reservoir, right? So there the potential difference is nothing but the difference in height. In this case, it's going to be difference in charge density. So what is charge flow? Well, charge flow again refers to how the electrons actually move, or how the balls move, how the candies move in this example. Now you can see that I've actually used a smooth tube to connect the reservoir and the box. Now if I have a material that is slightly more rough, then the balls are not going to flow out that easily. And that is essentially what resistance is, right? So resistance is going to hamper the flow of current, right? So for a given voltage, if your resistance is very high, then the current flow or the rate at which the charge flows is also going to be lower. All right. So that being said, let's just take a look at the animation first that we have made, and then we can kind of come back. So you can see that initially the jar is full of candy, and as I play the video, you can see that the ball starts to flow, and this is essentially what you would call as current. And as the jar gets empty, the potential difference is becoming close to zero, and when the reservoir is out of candy, then there is no longer any flow of new charge, right? So that is why when potential difference, current tends to zero as well. So that is why over time a battery dies, because the potential difference between the cathode and the anode essentially tends to zero. Now here you might have noticed that we have kind of explained most of the concepts. I'm not talking about capacity. So capacity is essentially the amount of charge or amount of candy balls that this machine can hold in the starting place, right? So here you can basically see that the balls are flowing at a particular rate. Say that 3 balls per second or something like that. And in 10 seconds, say that the tank is getting empty. So that means how many balls did we have? Well, it's 3 times 10, which is 30 balls, correct? So that is what you call as capacity. And here is an interesting thing. So if you have a capacity of 30 balls, you can kind of play with 2 parameters. What you can do is you can reduce the speed of the balls. So instead of having 3 balls flow per second, you can reduce the rate so that only 1 ball flows out per second. So in that case, it would take 30 seconds for all the balls in the candy machine to transfer to the brown box, right? And that is exactly how batteries work. Batteries have capacity, which is typically listed as amp hours. So essentially they can provide X amount of amps for Y amount of hours. So the capacity would be X times Y. Now, once you know the capacity, you have two variables to play with. You can make sure that you draw the current slowly so that you have the battery last for a longer time, or you can draw a large amount of current and the battery capacity is going to last only for a smaller amount of time. In other words, it's going to behave exactly like the candy machine. Now, need for DC-DC converters. So one thing that I wanted to let you know is, as the potential difference is draining, the current is actually dropping and the potential difference actually drops as well. But there are so many power electronics components in your vehicle which would require the voltages to be at a particular level. And that is where a DC-DC converter comes in. So as a battery is operating, its capacity drops over time. As the capacity drops, the DC-DC converter essentially makes sure that it steps up the voltage according to the requirements of a particular device. A DC-DC converter is very similar to a pump. So for example, say that you are pumping water from an underground sump. As the water level decreases, the flow rate is going to also decrease. But to a certain extent, I can achieve constant flow rate by actively increasing the pump power, right? And I can take it a step further and I can essentially have a sensor that measures flow rate, and I can basically have a controller which would increase the power so that the flow rate would be closer to the set point. And this is going to work till a particular level of water level, and at that point the pump might experience cavitation and the system might not work. But essentially that's what a DC-DC converter is. Okay. All right. So to kind of reiterate the example, the capacity of the candy jar is analogous to the capacity of a battery pack, and the flow of the candy balls is essentially like flow of charge, which is current. And the difference in density of the charge on the left hand side and right hand side is basically what you call as potential difference. So now that we have talked about the fundamentals of battery, the other thing that we need to talk about is the sources of heat generation in a battery. Now, why is this important? Since the course is eventually going to teach you how to design a battery thermal management system, you need to understand the sources of heat generation within a battery. And there are three concepts primarily. One is the internal resistance, which is essentially because of ohmic resistance. The second source for heat generation is the chemical reactions. Batteries at the end of the day produce electricity through chemical reactions. And you will actually later learn that there is a possibility for this chemical reaction to kind of run in an unbounded way, very similar to a chain reaction, which results in sudden increase in temperature. And this concept is called as thermal runaway, which is a dangerous phenomenon that occurs especially lithium-ion battery packs because they have a very narrow range of operation, right? So in order to prevent thermal runaway, you need to make sure that temperature variation across all the cells of your battery pack is kept to the required minimum. Okay, so we will be talking more about batteries, but let me kind of touch upon DC-DC converter. So what does it do? Well, it steps up or steps down DC voltage according to the requirements of any other onboard electrical devices. While designing DC-DC converters, the primary challenge is efficiency, making sure that the conversion process is efficient. And your DC-DC converters should be packaged to occupy the smallest possible space. And this is kind of true with most subsystems that are generally available in a car. You also need to make sure that the weight of the DC-DC converter is fairly low, or at least as low as possible. And another unavoidable problem is parasitics. Parasitics is essentially loss that's caused in DC-DC converters because of its interaction with various electronic components. Now, generally, how are these challenges overcome? Well, parasitic losses are geometry dependent, and usually 3D simulations are performed to measure the capacitance, inductance, and resistance of various parts of an hardware. And then once you do that, you can perform system level simulations to obtain the required current and voltage waveforms along with the parasitic losses. Then once you kind of do this, you can then kind of repeat the process, right? You can iterate the same concepts again and again till the performance and the losses are within the desired range. Now, as I mentioned at the start of the presentation, we will not be discussing DC-DC converters anymore in this course. The other key component that is used in electric vehicles is the electric motor, the traction motor. The motor essentially converts the electrical energy to mechanical energy. And with respect to the challenges, it's always about getting more efficiency and minimizing losses. Again, packaging is very important, and also making sure that the electric motor's weight is optimized helps in overall efficiency of the vehicle. Now, electric motors also have to be cooled. Again, it depends upon the size of the car, but if for passenger vehicle applications, your electric motors might have to be cooled. So you will have to integrate, or you'll have to make sure that cooling paths are designed and cooling systems are basically integrated with the electric motor as well. And how are these challenges generally overcome? Well, it's typically done by 2D or 3D simulations where Maxwell's equations are solved to basically perform an electromagnetic analysis on the electric motor. When you solve the Maxwell's equation, you basically solve for the magnetic field, and you can essentially determine the performance characteristics of an electric motor and also determine various losses that are typically found in the electric motor. So again, the process is very similar to what I mentioned in DC-DC converter. Once you figure out a reliable way to measure key performance parameters, you would modify your design. And for electric motor, this can be on the CAD side, this can be on the armature side, or this could be on the winding side. You have different configurations, and there are really powerful tools nowadays which can make your life very easy. And by using a template based system, you can design different iterations before actually building one. And just like DC-DC converter, we will not be discussing electric motor further in this course. Alright guys, with that I would like to conclude this video, and I'll see you in the next one. Thank you. Bye.